Hi everyone, welcome to Thermo. We are going to talk about property relationships today. This is going to be part one. So there will be a part two. Woohoo! But we are going to, number one, need your textbook. So either your physical copy, jump on the electronic copy, and open up to the tables that are in the very back of the book. It's the STEAM tables. And you'll see in those tables, the first set of, you'll see like A1, A2, A3, A4, A5, all those. So those are metric units. You want to jump to the A-1E, A-2E, A-3E. We're going to be looking at those today because we're going to be looking at English units. You're going to have to use the ones in metric as well, but today we are going to do English units. So I'll give you a little pause here. You can pause the video and grab your textbook, get open to those sections because you are going to need them right off the bat. All right, so first let's open up to A-2E. So here we have a temperature entropy curve. So we have our, again, remember what this is called? Vapor dome. So we are going to consider we're doing water. So that's those tables A2, A3, and 4 we will all be using today. There are other tables after that for other fluids other than water. So there's some refrigerants, there's ammonia. That's all off the top of my head. I can think if there's any more, but we're going to be using the water ones today. So in this temperature entropy curve that we have, we know from previous videos that this is an important point, and this is an important point. So here we have, this is where we're at a saturated liquid. I guess we don't have to do a subscript. Saturated liquid. And here, we're at a saturated vapor. So I want you to go to table A-2E. You can go to, it is a temperature table. This one is a temperature table. So you can go to 212 degrees Fahrenheit, and you're going to see that the pressure, which is the next column over, is 14.7 psi. So we are at atmospheric pressure when we have a boiling point of 212. So the saturated liquid point, this is right when it starts boiling. So if you go on that table, I guess I should say, we want these tables because we don't have gauges for these sorts of things. We don't have gauges to measure enthalpy. We don't have gauges to measure specific volume like we do for pressure. We can measure temperature and pressure, but it's not easy to measure specific volume or enthalpy or entropy. So we have tables for this instead of using gauges. So that's why you're going to use the table. So jump into the table, go to the temperature table, so A-2E. And I want you to look up, again, the temperature at 212. Pressure is going to be 14.7. I want you to look for the enthalpy columns for H. And I want you to find the saturated liquid enthalpy, which is going to be labeled as HF. And the saturated vapor, which is going to be labeled as Hg. So I'll give you a second, open to those tables, find those values. So based on this temperature and this pressure, we can determine that the HF, so the enthalpy for a saturated liquid, so that fully saturated liquid is going to be 180.2 BTUs per pound mass. So if you didn't get that, reevaluate, go back to the table, see if you can see where you may have went wrong. Maybe you got a wrong row, a wrong column. But that should be HF. The next one is going to be that vapor, that saturated vapor. So this is the point 100% of the water has boiled off. It's all vapor. And this is going to be an enthalpy of 1,150.5 BTU per pound mass. All right. And conveniently in the table, we have to do the subtraction a lot of times to figure out the difference between HF and Hg. And so they give us this value HFG, which in this case is equal to 970.3 BTU per pound mass. So this tells me, what this number tells me is that if I wanted to go from a saturated liquid to a saturated vapor, I would have to add 970.3 BTUs for every pound mass of water that I had. So this is useful. It's nice that they did that math for us. We have both of those values. But the question is, what do we do if we have a partially vaporized situation? So we have some still in the pot, but we have some as vapor. So there is an equation to be able to find that wet vapor. So maybe we're somewhere in here and we want to know what the enthalpy is at that point. We're not a saturated vapor, we're not a saturated liquid, we got to find somewhere in between. So we're going to use an equation. Let me change colors here. Let's go HWV. So HWV is going to be enthalpy of a wet vapor. And that equation is going to be your enthalpy for a saturated liquid plus some sort of X percentage. We're going to call X is the steam quality. Steam quality. So we're going to have X percent times by HFG. So what that means in terms of looking at this, so we have some sort of HF, and we are going to add some sort of percentage of that entire HFG, that difference between HF and HG. So say we had 20%, if X was equal to 20%, we would put 0.2 in there. So 0.2, it would be H of F, so 180.2, plus 0.2 times HFG, so times 970.3. And that will give us a wet vapor of 20% steam quality. So if this is 20% of the way across, basically you're getting that percentage. Something called interpolation. You can do this manually just thinking about the percent differences. A lot of times I go from saturated vapor down to that point. You can do it the opposite way as well. But this gives us our steam quality to give us that enthalpy for that wet vapor. And just think about if you were to try to find the saturated liquid enthalpy from this equation, you would just put 0 in this steam quality for a completely saturated liquid, and you just get HF. And if you were at a saturated vapor, you would be 100% steam quality. So you'd put 1 in here, which would be HF plus 100% of HFG, and you're just back to HG. So think about it in terms of that, how we would find something in between. It's very useful equation to be able to use that. But if we have pressures different than atmospheric, we have to take a little bit of a different approach to this. So I'm going to come down to this graph. So we're going to assume that this middle one is just this same line as up here. So this is our pressure is equal to 14.7 psi. And we know if we come across here, this boiling point is at 212 degrees Fahrenheit. And I know I made it a little confusing with those lines coming. They didn't have to come all the way down here. We'll go like this to try to get rid of some of that. Okay, so 212 degrees Fahrenheit. But what happens if we're not at the same pressure? So for example, what if our pressure is 40 psi? These are in absolute. So you're going to now have to go to table A-3E, and this is a pressure table. So you'll see in this table that the first column is pressure and then gives us temperature. So to practice this, go and find 40 psi for water and give me the temperature at which it would be a saturated liquid or boiling. All right, hopefully that gave you enough time. If not, pause now and find it. You should have gotten 267.26 degrees Fahrenheit. So if we have a higher pressure, we have a higher boiling point. And what happens if we hit this point at the top of the vapor dome? Go down to the bottom of the table and see what that pressure is. According to what I found, that pressure is going to be 3,230 psi, which is an extremely high pressure. This is actually called the critical point. I don't know where to write this. Let's put it here, I guess. So this is the critical point. And this is where water doesn't really behave like a liquid or a gas. There's a lot of research going on in this realm. If you're interested, look into it. We're not going to deal with it much here. But just so you know, the top of this vapor dome, critical point, stops behaving like we can predict easily with this vapor dome. Okay, so what happens if we go down to the lowest pressure? So if you go to the table again, go look what the lowest pressure is. According to what I found, that's about 0.4 psia. So 0.4 psia, if you go and find the temperature for a saturated vapor, what do you find for that temperature? I'm going to erase this here. Give you some more space here as you look at it. Okay, so what did we find for the temperature for this boiling point? I get 72 degrees Fahrenheit. That's really low. It's crazy to think about water boiling that way because I'm used to as well in Utah where I grew up. The pressure is a little different than this. It's actually lower than this. And so we have different considerations for a boiling point. So think about that. What kind of situation would this be where we can do 0.4 psi? So if we think about having some sort of hot plate, stove, whatever, and we have a pot of water on here, we have some water in here and we're trying to boil it off. If it's just sitting at atmospheric pressure 14.7 psi, we just have 14.7 psi pushing down on here, and it's going to start to boil at 212 degrees Fahrenheit. But if we were to put this in some sort of dome here, put our pot in here. Wow, that was a little crooked. So we have some sort of heat source again here, and we are trying to boil this water, and we have pulled pretty much a vacuum, 0.4 psi absolute. That's pretty low. So we're pulling a 0.4 psi vacuum. There's going to be a lot less pushing on this. It's going to have like a lot less force compared to this is a lot of force, and especially if we go up to something like 40 psi, we're going to have even more force pushing on there, and it's going to be a lot harder for the water to boil. Whereas down here at 72 degrees, these particles are going to start being able to vaporize. So think about that situation and why these these lines of constant pressure look the way they do on this curve. That's why. So here's atmospheric. Here's in a vacuum compared to that atmospheric. It's not an absolute vacuum. It's 0.4 psi, pretty close. So the moral of this story is the boiling point changes depending on what's pushing down. So depending on pressure. All right, so I want to talk about one last thing, and that is superheated vapor. So where that comes in, so this is what we consider SHV, superheated vapor. And where that puts us, I'm going to use this chart. That's going to put us somewhere up here. And so what this means is when we come across here and look at the temperature, maybe we're at 300 degrees Fahrenheit. Or we come up here and we're at 400 degrees Fahrenheit. And if you go to your temperature curve, or your temperature table, and look at 14.7 psi, that's way above the temperature of 212 that is associated with the temperature of 14.7 psi. So we're going to, again, have to pull out a different table. So for this one, we are going to use A-4 for E, and this is the superheated vapor table for water. And you'll see in there that each pressure has its own set of values. Or set of properties, I guess. So you'll see like blocks. It'll be like 14.7 psi, 20 psi, 30 psi. So you'll have that. So I want you to go to that table, and at 300 degrees Fahrenheit, for, let's still say our pressure is 14.7 psi A. What is our enthalpy? Do the same as well for 400 degrees Fahrenheit. So find our two enthalpies here. All right, so when I look at that table, I get an enthalpy of 1192. It's almost 93, 92.6. And that's still going to be in BTUs per pound mass. And the enthalpy for 400 is going to be 1239.9 BTU per pound mass. So I want you to think about why these values are. So at 400, we have a higher enthalpy than 300. More energy, it's a higher temperature. Makes sense. And I want you to think about saturated vapor, we had 1150.5. Okay, makes sense. We're still going up as we go. So start to think about those relationships of what that looks like in terms of enthalpy. And so the other thing that you may run into is, what if I give you, I have a superheated vapor at 310 degrees Fahrenheit. Oh, wrote that really small, 310 degrees Fahrenheit. How do I find H? Interpolation. So similar to what we did over here for quality, you can kind of think it in that terms, that you are finding a number in between here. So you're just going to have to do basically a percentage. If it was 350, it would be easy, right? You'd just do halfway, but we're at 310. So you're going to get to practice this a lot, but you get to do some interpolation to actually find that H value at 310. Or whatever value between 300 and 400. It is linear through the section, so you can do interpolation and you'll be okay with that prediction. So that is property relationships part 1. So we'll come back with part 2 and polish up a few things here. So bring your questions about property relationships part 1.